are going to start a new series of lecture on LHC physics. And I'm glad to introduce the speaker today, Professor Xu Shijie. He's currently at the University of Washington, Seattle. And he got his PhD position from degree from the University of California in San Diego in year 2008. And he then took the research position at the Lawrence Berkeley Laboratory, and as a Chamberlain Fellow from 2008 to 2012, and he got a position, the current position, in February 2013, and he's also a joint professor at the National Ching Hua University here. Okay. So let's welcome Professor Xu.
Thank you everyone. Yes. It's my great pleasure to be here to give a series lecture on the large result kind of physics. Actually, my supervisor of my master's degree is also sitting here. Yeah. So it's been a while. So I'm very happy that I have this opportunity to pass my knowledge to another younger generation to inspire you to work on exciting physics. So let's start with some brief outline. Of course, we need to make sure this works. Right. So I'll start with some big picture of the outstanding issue of particle physics, and in particular those we have hope to address in Hadron Collider. Then I'll give an introduction about Hadron Collider physics. And just, just to briefly comment on my background, I'm an experimental particle physics. So I knew that this is a special spring school for theorists. So I think it'd be nice that I could prepare a little bit more about the detector discussion. Probably you have a greater chance to touch that. So I prepared something I think is called the minimal knowledge about detector. So that could give you some preparation that you could interact with experimentalists, in particular in the collider physics field. So then I'll give a pitch about the CERN model and what we knew about the CERN model and the prospect of CERN model and beyond the CERN model. So if I have time, and I would also like to address about the program, the overall program that we want to move forward beyond the Okay, so I would like to give credit to other speakers that in this spring school series, also Summer Institute series in Taiwan. So I borrowed a lot of slides from them. It's quite difficult to go beyond these materials, but it's all helped me to prepare this lecture. Okay, so let's start with some big picture. So we are standing on the shoulders of these great giants in the science who move this field forward. This is a list of physics who direct or build either the theory or move the experimental frontier to develop our current knowledge of the CERN model. This is our current basic description of how the universe is made of and their interactions. So this is basically the simple cartoon like each of you are quite familiar with. And we knew that this simple picture now has been completely completed. We basically found every single pieces of prediction in this minimal theory to describe the universe. So one interesting is that if you look at the discovery of the particles that in the previous slide, all the fermions, which is the building block of matter, are found in America. But in terms of the gauge interaction particles, it's all found in Europe. Yeah? So there was a code before in Texas, which is called the SSC. It was one of 10 for America trying to break this symmetry. Probably they can try to identify this Higgs particle in US. Yeah. Due to many historical reasons, then now we know that this SSC is sitting there. But there's a code that probably we can try to revive it for another hadron collider pushing the differential frontier beyond the current LC. And I did not draw the picture in Asia, but we knew that in Asia we have a great achievement in terms of understanding of the CP violation sector of the flavor physics. And also, we also play a big role in neutrino here. Yeah. And in terms of the time-wise of the development of this center model, so we start with unification of the electricity and mechanism by Maxwell, and then starting from there, we jump into the quantum area, and here we actually learned that since the discovery of the collider, or before that we should call it the accelerator, we have a process of a huge number of new particles just maybe discovered in a weekly basis. So in that time, you can hear all kinds of new particles discovered. And that also give a birth of a particle data group, which is a big dictionary to collect all the information about the new particle discovered. It was used to be a small data sheet, but now it became a big book. So then, since then, we start building the more fundamental picture. All those discovered particles, they are actually not fundamental particles. And then this leads to a development of the center model. And now the question is that this center model actually have quite a list of outstanding issues that we are still not satisfied. And we want to ask further whether or not what's the even more complete theory to discover the universe. So I would like to just discuss each sector one at a time. So in terms of the matter building block, we knew that there is a fermions which builds this basic matter structure. And in terms of large hadron collider, it has a very special role compared to the other collider, for example, electron collider. It can provide extremely high energy, so it can easily produce the heaviest part, for example, tau, and start this property that cannot be done in electron collider. But there's also the caveat of this hadron collider. For example, neutrinos, it has many fascinating property. It has mass, and it also have this mixing property. Unfortunately, large hadron collider is not the detector can directly probe this kind of property. However, if we want to explain what's the origin of the mass of neutrino, then we have learned from Stephen's excellent lecture what kind of basic model you can build to describe that. And many of these can actually predict some kind of new particles in order to complete those theories. And large hadron collider have a chance to probe this kind of neutrino model if the neutrino is actually around PeV scale. So I will cover that in this lecture series. Okay, so then nevertheless to say that instead, other than the neutrino, that it has the mass that we cannot direct study in large hadron collider, all the other sector of the other sector of basic Chicago Park, we concluded that we knew it very well. Then we built from this kind of knowledge, trying to push forward the knowledge frontier. I'll move on to the gauge boson sector. So this interaction has an interesting property. It's all spin-one particle. And it's been a long time that for 35 years that other than the spin-tail particle or the spin-one fundamental particle, there's no other type of spin of a particle exists in nature. And then one of the things that LHC can do with this kind of interaction particle is that we have a large data we produce, so we can try to probe the gauge structure of the EH-weak interaction and or the QCD sector through this study of the extremely rare production. Because those rare production usually come from the loop. Then if we have new physics, they could have a chance to show up from the study of those rare production. And then if you study those rare production, and we also learn from Stephen that if you have a new field scale, it's very high, then you can easily reduce that to describe that with an effective field theory. So by studying those, then you basically can study the dynamics of the new physics at a very high energy scale. So of course, then we have to move on to the Higgs. And now, since 2012, basically we have verified that we have a brand new object, fundamental particle in the world, which is a spin-zero particle. It's the first particle we ever found by humankind in the universe that it has spin-zero, completely different from what we learned as spin-half and spin-integer particles, spin-one particles. Yeah. So it was used to be which is the highest priority mission, which is we want to find it. Yeah. And then this is just an interesting timeline that on July 4th, that 2012, we announced the discovery of the Higgs. Then on March 14th, so I consider this another milestone, which is CERN collect all the study of using all the data we have from ATLAS and CMS to study the property of this particle. And we have a relative soft element. It's a little bit stronger now. It's more and more like Higgs boson. So why this is interesting? Because there's a long list of data behind that trying to promote. We should consider to award the Nobel Prize to acknowledge this big achievement. And I think Nobel Prize committee they listened to this statement. So in October 2013, Engler and Higgs they are awarded the Nobel Prize because of their work of the theoretical framework of the prediction of this Higgs particle to explain the electrosymmetry breaking. So the mission is completed. We have accomplished one of the major missions of a Large Hadron Collider. And this is really exciting because if you think about that, we actually did not run Large Hadron Collider in its designed configuration. We only run on half of the energy of this machine. And we even not reach its design luminosity. And we already have this big achievement. So there's a reason for us quite optimistic way that we have a chance to produce more exciting results. So what kind of exciting result we think we should try to search for? In the linear list of options, there's a possibility that actually probably nothing beyond the third model except this new discovery happened. Yeah. So this is actually a little bit the worst scenario, but we have to consider all kind of possibility and make a scientific judgment. So in some case that as a scientist we need to be optimistic, so we can try to push the program forward. So we could have discovered of a new physics beyond the model, and in three major different ways. One, we can study the Higgs property to a very high precision. It's a production rate, it's a decay branch ratio, and if we find any discrepancy, that's clearly that will give you a window toward the new physics. And or not necessarily Higgs, yeah. As I mentioned earlier, that you try to study the other cinema process in high precision. Once you find discrepancy, then there's also a window toward new physics. Or even more exciting, we found more than this scalar, this spin zero particle. It's some new particle that some new resonance at higher energy scale. So we could also make a further progress on understanding the dark matter in Large Hadron Collider for different kind of dark matter scenario, and we can probe that cannot be probed using the low energy experiment. So in terms of thinking about the new particles, so one major way is that we have three different types of fundamental particle in our universe. So fermion, yeah. Then it's not necessary that we only have 6 quarks and 3 family of leptons. There could be just a new type of fermions. For example, we could have basic vector-like particles. Or if we look at the gauge sector, it's not necessary we only have this W plus W minus, Z boson, and photon or gluon. There could be just a new gauge fields. It's W prime, Z prime that exists in the nature. And or there could be a new scalar. So in the minimum Sunday model, it predicts a single spin zero particle, but a minimal extension like a 2 Higgs doublet model, it predicts 4 extra Higgs particles. And one of them is a pseudo scalar Higgs. The other is just also spin zero particle, but just much heavier. So the new physics could also show up in this case, yeah. Or just some new particle that not fall into this spin health, spin 1 or spin 0 category. Some new particle, for example, graviton, could have spin 2. So if you think about you want to build a picture or trying to develop a model or theory to probe, you will fall into either one of the category. And in terms of the conceptual extension, which is when you guys trying to build a complete theory to explain or to match to the quantum field theory and make it realizable and make it to be a theory trying to probe one of the big questions. And this kind of conceptual extension, we have kind of 2 famous branch that has been exist for 35 years to address this electrical symmetry breaking. So one is that the supersymmetry, that it's a weakly coupled theory that every fermion have corresponding boson partner, and boson have fermion partner that under the supersymmetry you can rotate and convert one to the other. So, or you could have a strong coupling dynamics that candidate theory, for example, technicolor and the over HR dimension. So those kind of strong dynamics, basically, in other words, they say the Higgs could be not a fundamental particle, it could be a composite particles. So the spin zero could be composed of two fermions, or the original prediction for Higgs color is being quite emphasized that there could be just no such low mass particle exists. Of course, now we know we exist a Higgs particle. So I'll try to come back to this theory later. But there could be something else that we have not ever thought about. So there will be a request from experimental this point of view that theories could apply your creativity and imagination go beyond these two branches to have a breakthrough of the theory. So these caveats on those two big family. Yeah. So first, we knew that if you look at all the current experimental data, many experimental tests of the Standard Model is actually overwhelmingly successful. So right now, we can say that you cannot find a real discrepancy between experimental data under the Standard Model framework. So now we have observed this new scalability, and the 125 GeV mass, this is actually a very interesting observation, which is if you look at the supersymmetry, actually it's uncomfortably high for the minimum supersymmetry. And if you look at the strong dynamics theory, it's uncomfortably low for this scenario. So the observation of this particle, and also the fact that the nature give us the observed mass at this value, at some point also give us a lot of interesting discussion right now. So is that true that the two major family of the explanation of the electrical symmetry, they might not be just the fundamental simple theory to explain this. So it still gives a lot of homework to do. So other than this electrical symmetry breaking, then Stefan had already addressed at least several open questions in his internal talk. And here I try to make a list of these open questions that Large Hadron Collider have a way trying to probe some of them. Okay, so for example, let's start with where did the spectral particles come from? So we have this three family of the quark lepton, and we have also the H group define the interactions. So how this spectrum come from and how the quantum numbers show up, how they are generated. These are the open questions for the Standard Model. Yeah. Then what determines the electrical scale? So this is now we have a first step. We have Higgs mass at 125 GeV. So we have some guidance now how to move on to the next step from this value. And where did the Ikawa coupling come from? So basically, the original setup of the Standard Model, we learned that it actually just tried to attempt to explain how the gauge boson get mass. And in terms of the origin of the mass of the fermions, and its Ikawa coupling form, the fermion coupling to Higgs, is kind of ad hoc. So you don't have a real fundamental origin, like a motivation of why you do that. It's just now it's just put it there. So you could play this kind of Lagrangian term to play different way to generate the mass of the fermion. But what is the most fundamental picture, and what's the most appealing motivation to do that? Those are the open questions. And then we have also learned about hierarchies. And hierarchy, in one way, we can say that we have seen a huge order magnitude difference of the mass of the quark sector and also electron sector, or even the CKM angle. You can see this is a huge difference. Some of the angle is very small compared to the other. And Stephen also addressed the strong CP problem, that, and also the electric scale and the Higgs mass compared to Planck mass scale. So this kind of a huge range of the automatic difference of the fundamental parameter of a standard model. This is a big puzzle of why the nature behave like that. So, and dark matter, this is clearly something beyond standard model. That's how we can rewrite the standard model, so write a more complete theory that also can explain, give a consistent, a big picture of the dark matter. And neutrino mass and the missing angles, that has been covered by Stephen. And so all these, actually, all of these big questions and also the setup of the standard model, what I described so far, they have been developed and have been known since the late 70s. So that means even before you guys existed in the Earth, before you were born, people have been talking about this kind of big questions. Okay, so have we made any progress in the past 35 years to understand these kind of big questions? Yeah. So let's start with looking at some experimental progress. So what we learned is that, at least compared to 30 years ago, when the standard model was first formulated, at that time we still have a couple of many parameters we don't know. And now all these parameters, like the mass of the double boson, Z boson, the mass of all the quarks, and the mixing angle of all the quarks, and also most recent the Higgs mass. So now I can say that all the parameters required to complete the standard model has been measured. And we also learned that neutrino mass is non-zero. So, and in particular, the three missing angle of the three family neutrino has been measured. But yeah, I should not include that because it clearly is something beyond standard model. Then we now know a little bit more about the dark matter. So there are also a lot of exciting progress on the dark matter that we now learn more about the nucleon interaction cross-section as function of different dark matter mass candidate. So we have pushed the frontier to more, even now, very close to the radic density predicted nucleon interaction cross-section. So all this has been accumulating in the past 35 years. And we do, following this standard model framework, we, in the experimental side, we have made big progress trying to address most of the parameters. And the dark energy is actually something beyond standard model that we don't know how to fit into that yet. In terms of theory, so mostly the development theory not directly related to the experiment in some way, because the big fundamental theory has been formulated quite a while. However, in past 35 years, we now have a better understanding of quantum field theory